Right. So, hi guys. So we have one more part left, and that's basically if we have an IEEE single floating point value, we need to again um, create the decimal representation out of it. So that's the last step. I'll be using, so let me take a look where I had this result. Um, I'll be using one of the results we had. Where is it? Of the addition. So yeah, so remember that we did the addition. We had this result. So C was 0, 1, 0, 0, 0, 0, 0, 0, then 0, 0, and then a repeating part. I'll be using this value as a value that I want to convert back to decimal. All right? So it's one that we had. So I'll just write it back down again here. So C was 0, and then 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0. All right. So there are a few things that we need to do to be able to extract all the information. So again, make sure that you bring markers during the exam. It's way easier to, like, instead of writing it like this, if you get it on paper, it will be grouped per 4. So maybe not in this format. So you have to count 1 bit, then 8 bits, and then 23 bits. You can just use markers to just mark them. It's easier so you don't make any copy mistakes. So what I need to do again is I will be extracting all the information that I have here, which is basically the sign bit of my value I get, which is a 0. So I already know it will be a positive decimal value. It's easy as that. I have my exponent, which is 1, 0, 0, 0, 0, 0, 0, 0. I will unbias this again, so this is 128. I'll subtract 127 out of it, which gives me an exponent of 1. And then I have my mantissa, which is this big part here. Now, to convert back from IEEE to decimal, we'll be using a formula where we will plug in 3 parameters, which is basically our sign bit, our exponent, and also our mantissa. But it will be the decimal representation of this mantissa here. And to be able to calculate this, we will need 2 steps. Because it can happen that maybe you can skip one of both steps. Most of the time is the first step. But so what we have basically is we can have a repeating part. So we see that in this case we have this part that repeats itself. We need to know what one part of this, so this nibble in this case, this part, what does this represent in decimal value? And then the other thing that we have left, and that's step 2, is the non-repeating part. So you will probably always have a non-repeating part, unless it's all zeros, of course. But this can be optional, right? The repeating part can be optional based on the fact if it's a finite or an infinite number representation. So step 1 is calculating the repeating part. So the repeating part, what does it represent in decimal? So to be able to do this, what we need to do is we need to take one of those repeating parts. So in this case it's 0, 1, 1, 0. I'll calculate its decimal representation, which is 6. And I will divide it again, just like I'll divide it by the next most significant value, or bit representation, which is just like with the rounding. So in this case it is 1, 0, 0, 0, 0, which is, of course, 16. So I know these 2 values, right? What I do then is I say I will divide 6 by this value 16, but we need to have a few things extra in the formula. First of all, we have a rule that in infinite geometric series that you need to divide it by the next most minus 1. So basically it would have been, so minus 1, basically it would have been the same that I divide 0, 1, 1, 0 by 1, 1, 1, 1, by all ones. Yes? So it's 16 minus 1. So this gives me 6 divided by 15. We are almost there though. There's one more thing that we need to take into account. We have a repeating part. Now I said we had two parts. We had a repeating part and a non-repeating part. To be able to know what it represents, the repeating part, we need to already know where it starts. So we know that we have 3 bits that are non-repeating. We need to take this into account. We need to take into account where its location is inside this mantissa. So we will divide 6 by 15 times 2 to the power of the amount of bits we have that are non-repeating. So in this case, it's 3 bits. So we'll divide it by 6 divided by 15 times 2 to the power of 3. 3 being the amount of bits that are non-repeating. By the way, one more thing, the -1, don't forget it. You'll see that for the non-repeating part, we won't be doing the -1. So here there are two things, it's -1 and it's 2 to the power of the amount of bits of the non-repeating part that you need to take into account. Or basically what we say here is 6 divided by 15 times 8, or 6 divided by 120. And so for the people who are not able to do this kind of division, you can again use longhand division. So I can write down 6, and I can write it as with a fractional representation, 6.00000 divided by 120. And of course then you just do the longhand division. How many times does 120 fit into 6? 0 times. So -0, I keep the 6, I drop the 0. How many times does 120 fit into 60? 0 times. I'll subtract that, I'll keep the 60, drop the 0. How many times does 120 fit into 600? Well, 5 times, which is exactly 600 as well. I have a remainder of 0. We found the result. So this is of course 6 divided by 120. The result is 0.05. So this is the result of our first part, the repeating part. The second thing that we need to calculate is the non-repeating part. So non-repeating part. And what we have to do here is, again, the same thing. We take the bits that represent the non-repeating part, and in our case, for this moment, it's 0, 0, 0. And we divide it by the next most significant representation, which is 1, 0, 0, 0. And we don't do -1. So in this case, it's 0, this is 8. So it would have been 0 divided by 8. So not with the -1. So in this case, it would have been -0. But of course, we know that 0 divided by 8 will be 0 as well. So in this case, the non-repeating part, is not that important here. But so, for example, just for example, it has nothing to do with the calculation we are doing, but I want to show it anyway. So for example, it could have been that it was 1, 0, 0, and so then we just divided by what we just had, so 1, 0, 0, 0. So the next most significant, it would have been 4 divided by 8. Without a -1, it would have been 0.5. For example, right? So this has nothing to do with the calculating we are doing at this moment. But this could have easily been the representation of the non-repeating part. And then the third step is the one that we plug into the formula. And that's the one that you need to know, of course, to be able to do the conversion. And so the formula is as follows. It is, before you do the plug it into the formula, what you need to do, of course, is add both parts, step A and step 1 and step 2. So you do step 1 plus step 2 to get the mantissa that you need. So in this case, it is 0.05 plus 0, which is 0.05. So it could have been 0.55. But in our case, it's this. So this is the mantissa decimal representation that we need for the formula. And so the formula, again, is -1 to the power of our sign bit times 1 plus the decimal mantissa that we just calculated times 2 to the power of our exponent that we have. So this is the formula. You need to know this one. And so here we have basically 3 parameters that we need to fill in, which is the sign bit, the decimal mantissa, and the exponent. And so in our case, it is -1 to the power of our sign bit, which is 0, times 1 plus the mantissa, the decimal mantissa we just calculated, so the addition of both the repeating and non-repeating part. In our case, it's 0.05, so it could have been 0.55, like I mentioned already, times 2 to the power of our exponent, and our exponent was 1. Or, let me make this a little bit easier to read, -1 to the power of 0 is, of course, 1 times 1.05, just add both of them, times, of course, 2 to the power of 1 is 2. Or in this case, I think it's not that hard. 1 times 1.05 is 1.05, times 2 is 2.1. And this is the result of converting this IEEE value to the decimal representation. And if you recall, of course, where is it again? We did this addition 0.85 plus 1.25, which is, of course, 2.1. So, there you have it. There is no difference between an infinite or a finite number, just the fact that based on infinite or finite that you will have to do the repeating part or not. But the formula stays the same. The thing here stays the same as well. Just don't make the mistake for repeating part. You do the -1 for the part that you use, so this, the next most significant -1 for the infinite geometric series, and you multiply this by 2 to the power of the amount of bits you have before the repeating part. And then the non-repeating part, you don't do anything. You just divide by the next most significant. You don't subtract it. It's not an geometric series. It's not repeating. And of course, you don't need to take into account where it starts, because it starts it starts at position 0, so it would have been times 1, which of course makes no difference. Right, so I hope this helps. The only thing I can say here is practice. Practice enough, practice a lot. It's important to practice. It's something you have to get used to. Use all the tools available on the internet to validate your results. You can use I don't think you can use the regular Windows calculator, but there are some tools on the internet as well as on smartphone. So there are a few things that you can use. Let me quickly check something for you guys. Yes, so, well, I use 16 free, for example, to validate. For example, well, I had the 125. I can see IEEE, and I can see the sign bit, the exponent, and the mantissa, as well as the hexadecimal representation. So you can always validate your answers yourself. So I could give you a bunch of numbers and some answers, but it's pretty useless. You can take any 2 numbers and do the entire thing. So practice, make sure you know the rules. I think it's not that hard. It's something you have to get used to, and that's it. Right, so if you have any more questions, feel free to contact me or post some comments here below. Thanks.